Okay, so let's talk about the demystifying the title, restoring natural capital. Natural capital is a relatively new concept. Actually, the concept itself is old, by the idea of calling it natural capital and bringing it to mainstream economics, relatively new, something from the 90s. And the idea is that the integrated societal wealth is composed of three things: natural capital, produced capital, and human capital. Natural capital being all the renewable and non-renewable sources that are in nature, like forest, water, clean air, clean water, fossil fuels. Produced capital, the machinery, the buildings, the infrastructure that we have, and human capital, things that walk out of the door with us, our knowledge, our skills, our capabilities. So 10,000 years ago, natural capital was plenty. Nature was there, was ours to take. Whatever we did 10,000 years ago didn't change the amount of natural capital that was available. Over time, we started consuming the natural capital to a point that today, 47, 48% of all original ecosystems were converted to human use. And possibly 90% of the ecosystem have been disturbed in a way, in some way, by humans. In 2020, El-Hasham et al. Published this article in Nature, which is a fantastic article where they managed to calculate the mass of all human-made things and compare it to the mass of all living things, all the biomass. And at that time, 2020, they were equal. The mass of human-made things were equal to the mass of all living things. But if you go to look at the details, even more staggering. The mass of plastics is 2 times the mass of all living animals, from ants to whales. The mass of buildings and infrastructure is bigger than the mass of all trees and shrubs on Earth. And this is not without consequence. If we look at a framework called the planetary boundaries that looks at what's a safe space for Earth to operate, by looking at 9 different processes that are life-sustaining, we have transgressed 6 of the 9 processes. We are in the risk, with the safe area would be the green space. We have gone out of the green space in 6 of the 9 processes, 5 of them directly related to land use. So just preserving what we have in terms of intact ecosystem is not enough to maintain the biosphere stability. We have to restore part of it. We have to reverse part of the conversion to human use. So climate change is just the most visible symptom of the depletion of the natural capital, but it's one on which there is a good consensus. And so pursuing net zero in terms of emissions, of CO2 emissions, pursuing net zero may be the right driving force that we need to restore the forest biodiversity and resilience of the biosphere as a whole. So many of you probably saw this graph before. This is the most publicized graph from the IPCC report from 2022. They show 4 different pathways. The red one is what happens if we do nothing, business as usual. And we will continue to emit the same amount of CO2 for the next 3 decades. And this is going to be disastrous. This is really, we're talking about here in a scenario where we're probably going to have a global warming of 4 to 6 degrees Celsius. The other 3 are pathways designed by looking at 1,200 scenarios in which they vary the timing and intensity of policies. But the scenarios, they don't have any distinction between what are the alternatives that we're pursuing. So Lamb et al. In an article published in 2024, took the 1,200 scenarios and divided them in three buckets. Scenarios that had an emphasis on demand reduction, slowing down the economies, consuming less, using less energy. Scenarios that had focus on renewables, a quick transition from fossil fuels to renewable sources. And scenarios that had a focus on carbon removal. So heavy reliance on carbon dioxide, CDR, removal, and a delayed fossil fuel phase out. Not because delaying fossil fuel is good, other than good for the industry, just because it looks very, very hard to change behavior and habits and reduce fossil fuel consumption. Now, this is from the same article, and here the first box is the situation we have right now with all the emissions. The first one is basically methane, the pink one. The other ones are fossil fuels, all the way down to the brown one, where you have land use, the emissions from land use. And what's below zero are carbon dioxide removals. And at this point, the only one considered here is nature-based carbon dioxide removal. They represent 99% of the removals happening today, and that's 1.6 gigatons of CO2. Now, the box on the right is net zero. It looks at the net zero, when we're going to get to net zero of all greenhouse gases, including methane. The one in the middle looks at when we're going to get to net zero, looking just at CO2. For the purpose of the discussion, the middle one is more interesting because there's no way to remove methane from the atmosphere. Methane is counted on parts per billions in the atmosphere, and there's no known process to try to capture methane. So if we want to discuss what are the strategies that we want to use to reduce emissions or remove carbon dioxide from the atmosphere, we should probably look at the box in the middle. So in the box in the middle, you see those same three buckets that we talked about: the demand reduction, focus on renewables, or focus on carbon dioxide removal. And you look at the year in which we get to net zero, the one that brings us to net zero sooner is focus on carbon dioxide removal. Now, this doesn't mean that this is a license to emit more. As you can see, there's a big drop on emissions on all scenarios. It's just that at one point, we're going to have to start making economic decisions. Is it better to reduce to zero certain emission, or is it better to continue to do something and remove it in another way? Another benefit of the focus on carbon removal is that you get to net zero with a strong infrastructure to continue to remove carbon dioxide from the atmosphere in the years going forward. So we have a better chance and a better infrastructure to continue to reduce the CO2 level in the atmosphere from levels that are lower than the levels that we're going to get in 2047. Now, to have a yardstick to decide whether we should reduce in the last mile, if we should continue to reduce in the hard-to-abate sectors the emissions, or if we should emit a little bit more but remove, we need a yardstick. We need economic comparison. So this is the idea behind the social cost of carbon. The social cost of carbon looks at what's the damage caused by 1 ton of CO2 that's emitted to the atmosphere. It's an incredibly complex calculation. First, you have to calculate what's the consequence for warming of 1 ton of CO2 in the atmosphere. Then you have to calculate what are the consequences for climate. Not only the immediate temperature, but the whole consequences in the atmospheric circulation, ocean circulation, and everything else. And then you have to go back and calculate what kind of damages you're going to be suffering from that change in climate. impacts on agriculture, the impacts on industrial productivity, the sea level rise, health, death, climatic disasters. So this number has been calculated for a long time. In 2015, in the Obama administration, the EPA issued the number of $36 per ton of CO2. So this would be the damage caused by 1 ton of CO2 emitted, and also would be the benefit of capturing 1 ton of CO2 from the atmosphere. When Trump took office in 2017, in the first month, he changed the assumptions and reduced the number to 7. So instead of causing damage of 36, the EPA resolved that the damage was just $7 per ton. Obama took office in 2021, resumed assumptions from the Obama administration with new findings from science and economics. The number went up to 51. And at the same time, Biden commissioned a group of scientists and economists to study the social cost of carbon and come back with a complete report. The report came out in 2023, and the number was 190 per ton of CO2. Pretty much at the same time, an article came out in Nature with a meta-study, look at all the studies around the world that try to calculate the social cost of carbon, and the number was 185. So there is a strong consensus around this number. 1 ton of CO2 emitted in the atmosphere causes damages of around $190. There is an outlier, a report that just came out from an economist in Stanford, Adrien Bilal, proposing a number of almost $1,400. And the reason for the number that's an outlier is because he looks at climatic disasters that are caused by climate change. And as climatic disaster can hit anywhere, including very rich countries, the damage is much higher. Typically, damages from global warming are more severe in poor countries in the global south than they are in the rich countries. But if you count for climatic disaster, this could change, and that's the reason behind this report with an outlier. But the number that is more of a consensus today is something around $190. So this brings us to an interesting calculation. Let's look at 2 different uses of fossil fuels. The first, coal power generation. 1 ton of coal produces 2.5 megawatt hour of energy. This is valued by society, how much we are willing to pay for 2.5 megawatts hours of energy at $125. At the same time, burning 1 ton of coal generates 2.5 tons of CO2. If you use that number, the social cost of carbon, that's $462 of damages, meaning that every time we generate energy from coal, we're setting humanity back on $337. Humanity as a whole is losing $337 every time we use 1 ton of coal. There's no way we're going to fix this with removal. We just have to stop emitting CO2 from coal generating power generators. There's no way we're going to reverse this. Let's look at on the other end. On the other end of the spectrum, you have commercial aviation. A flight from New York to London on a Fission airplane, Airbus 350, has revenues of $350,000. Again, that's how much society values this service of flying to New York to London. It emits 128 tons of CO2. That's $24,000 of damage. So a 6 or 7% increase in the price of the ticket can generate the money that can be used to remove CO2 from the atmosphere. So it could work. The question is, can we remove CO2 from the atmosphere at the $185 per ton? So this is a study by McKinsey, published in 2022. It looks at all the technologies and the prices, first bar today, second bar in 2035, third bar in 2050, and the size of the bar is the uncertainty that we have for the price. So if you look at 2050, all technologies are either below the 185 bar or have a fighting chance of getting there. And chances are that if there are incentives, if they have a chance of learning by doing, all of them are going to be below $185. So there would be a big supply for removing CO2 from the atmosphere if the price was at 185. Now, but there's another complication. When we emit a CO2 molecule into the atmosphere, it immediately mixes into the atmosphere and becomes indistinguishable. All CO2 molecules emitted are alike. They are fungible. But each CO2 molecule that's removed, it's removed in its own way. The process and the way that the molecules is stored after removal matters. Okay. Maybe analogy here, if you think of the CO2 in the atmosphere as cash, so cash is fungible, a dollar is a dollar, but when you remove it, it's something like buying a bond. Bonds are different. They can have a different term duration. They can have different interest rates. They can have different risks. So you're taking the CO2 from the atmosphere and you put it into something like a bond, a saving account, an investment, and everything is different. So we have to look at, if we remove the CO2 from the atmosphere, how did we remove it? And we can go back to the various technologies. The ecological restoration is growing forests to remove CO2. Bioenergy with CCS is capturing the carbon when you're generating biofuels, for instance. Direct air capture is capturing directly from the air with machines that do just that. Biochar is producing something that's very close to coal, pure carbon from biomass, and that's very stable. And enhanced weathering is a new technology that is been picking up in the last couple of years, which is basically using rocks that can absorb CO2 and using them to fertilize soils. So they're all different, but let's look at two extremes. In the left here, you have the largest direct air capture equipment in the world. This is in Iceland, it's called Mammoth, and you can see two small people there in yellow. That's the size of the equipment. This equipment captures 39,000 tons of CO2 per year. It's equivalent of 2,000 to 3,000 hectares of forest. So it's a huge equipment for the amount of CO2 that it can capture and uses a huge amount of energy. On the right, you have an operation of ecological restoration. And those are pretty much the two extremes in terms of most technology and most novel technology and most well-established technology. Now let's compare those two. I think the three elements for comparison, I talked about the bond. The bond has interest rate, thermal duration, risk. If you want to compare ways for capturing carbon, I think the three most important things are additionality, permanence, and leakage. Additionality is whether or not that carbon capture would happen in the absence of a market, of a price for carbon. And I think the answer for direct air capture is an absolutely yes. It has total additionality. Nobody would put up an equipment like that in the middle of nowhere for other reason than capturing carbon and selling the credit of having captured the carbon. So it has perfect additionality. Ecological restoration, it depends. If you buy a cattle ranch that has been a cattle ranch for generations and would continue to be a cattle ranch for generation, and you buy it for the sole purpose of bringing back a forest in that space, and with growing the forest capturing carbon, yes, it has additionality. But land that has been just abandoned and where the forest will also grow in an abandoned land, there's no additionality because it would happen anyway. So It's a complicated concept, but it's critical because we are right now, for every two molecules of CO2 that are emitted into the atmosphere, only one stays in the atmosphere. The other one, it's captured by the natural system of the carbon cycle on land or ocean. So carbon capture is happening all the time everywhere. The question is something I'm doing right now additional to that? So that's the question of additionality. Permanence is for how long I'm going to keep the CO2 molecule away from the atmosphere. In the case of direct-to-air capture, you can build the system in a way that you store it for millennia. You store it underground in a safe way with a well-engineered system, and you're going to be there for millennia. In the case of a forest, it can be there for millions of years. Tropical forests have been around for millions of years. It's a dynamic system that can adapt, can evolve, so it can be there for millions of years. But it can also catch fire. It can also be cleared down again. So the permanence depends on the design, on the laws, and the regulations. But then it costs $500 to $1,000 to capture 1 ton of CO2 with direct air capture, basically because of energy cost. And ecological restoration, 1 ton of CO2 can be captured for $20 to $80. So other consequences, direct air capture are mostly negatives because they are very energy intensive. And energy is one of the causes for emissions, so you're adding to the problem in a way. In the case of ecological restoration, the side effects are generally positive. You promote biodiversity and other ecosystem service. Direct air capture is not ready. It's still a lot of technological issues, including the amount of energy it consumes, but also the amount of chemicals. Ecological restoration is absolutely ready. We have been doing this for 200 years at least, the active restoration of ecosystem. Scalability, it's easy to scale if we solve the problems of chemicals and energy. You can scale direct air capture to an unlimited size. We can capture as much CO2 as we would like if energy is not a problem. Ecological restoration does have a limit. It uses land, and land is a scarce resource and competes with food security, with water availability, with other bioproducts. Any questions? How are we doing here? Okay. Okay. So let's get into Regreen. So this is a company I founded. I started this project roughly 5 years ago. The company was really founded 4 years ago. And the original idea came from a paper published by my other co-founder, Bernardo Strasberg, in Nature in 2020, where building for that idea that we were discussing, that ecological restoration is a very effective way to capture carbon. You saw the price, $20 to $80 compared to $500 to $1,000. It's ready, technology is there. So the question he came up with, if we were to restore 15% of all land that was converted to man use, to human use, where would I do this? Where are the places where I would get the best bang for the buck, the most results for the same dollar invested in restoration? And the conclusions were very interesting. He found out that if we converted the right 15%, the best 15% on Earth, to the original ecosystem, we could capture almost 300 gigatons of CO2. That's 1/3 of all the CO2 that was put in the atmosphere since the Industrial Revolution. And we could avoid 60% of the expected species extinction. So promoting biodiversity in a big way.
I don't know if you're able to talk about this, but what is uncertainty around those numbers? Like, I mean, 'cause I imagine they come up with some
Yeah.
model.
They, well, first, there are many, there is a big uncertainty in the numbers, and there has been a lot of debate around the numbers. But as we moved into doing the restorations, we are confirming most of the numbers in terms of how much carbon can be sequestrated for the amount of land used. So there's not much uncertainty there. There's obviously a huge uncertainty in the extinctions, how many extinctions, species extinctions we're avoiding. What he's using here, Bernardo, is basically the habitat as a proxy for how many species would be extinct and how many species would avoid extinction given the increase in habitat for that species. And now there are other articles coming from looking at this problem from different angles. Cesar Tejer, for instance, has a fantastic article where he looks at the same thing, but prioritizing for water availability. And he comes up with even bigger numbers for because he calculates also if we were to optimize for water availability, not restoring in places where you would create water scarcity, not restoring too much that we would risk water availability. How much can we restore, and what would be the carbon sequestration? The number is even bigger. Business model. So based on that article, that there was a big opportunity for selecting the right places for doing the restoration, and this could be very efficient. We set up to create a company and that had a vision that instead of generating wealth as humans have been doing for the last 10,000 years by deploying nature, we wanted to prove that we could make money, we could create wealth by restoring nature, by reviving nature. And that ties up with the concept of natural capital. If natural capital is something that we value, restoring natural capital should create value, should create wealth. That's the big vision. The goal is to restore 1 million hectares. One hectare is 2.5 acres, capturing 15 million tons of CO2 per year. Yeah. And we base, and the company was based on good research, and we set up the company to be the best in class in R&D and a company deeply grounded on science. We decided that we would only make what we call 5-star restorations. It's a definition by the Society for Ecological Restorations that give the guidelines for restoration to be 5-star, meaning that it protects biodiversity, it benefits the local community, and it provides other ecosystem services. And it's as close as possible to the reference model, the forest that would exist there if the forest hadn't been cut down decades or centuries ago. We get our revenues from sale of carbon credits and some sale of native hardwood that we overplant in the restoration in order to cut down some forests during the process of restoration and sell the hardwood. To scale to 1 million hectares, we need to create all the supply chain and all the processes within the company to be able to scale. Again, this has never been tried before to restore 1 million hectares. So we had to think about how do we create all the phases of the process in order to be sure that we could scale up the process as we go. And the phases are land procurement, restoration planning, restoration execution, and integrated monitoring. Let's take a quick look at some of them. This comes directly from the paper that I showed, the Bernardo paper. He did this on a global scale. Where should we restore to have the most benefit in terms of carbon capture and biodiversity? We took this to a granular level. So we took the map of Brazil. We operate only in Brazil. We took the map of Brazil and we went to the real granular level of property by property, land plot by land plot, and we looked at, for that specific plot, the land use, current and past land use, the topography, the type of soil, the climate, the microclimate, the water availability. We put all this together, and the model generates a proposed restoration model with all activities that we should have on the plot and the cost of each one of the activities. We then compare this with how much carbon is going to be captured by that restoration and decide whether or not that restoration would be economically viable. If it is, we try to acquire the land plot. We have been doing this for 4 years. We already analyzed 3.7 million hectares, and we bought 27,000 hectares and leased another 6.3 thousand hectares. That not to say that we have a funnel that we have always to start with 3.7 million and end up with 27. There are many different reasons why some areas are still in the loop and they have not come out of the process as acquired land. It includes land title. We don't have the right technology to do it. They are too far away from the other properties and we don't want to move away from a cluster. So this is a living cycle that will continue to put more properties into the pipeline and bring more properties out. But 27,000 hectares is already a very, very big amount of restoration. That's a total area we have bought. We have already restored 13,000. And this is an example of types of restorations that we do. We have more than 60 types of restoration. When I talked about the model looks at the conditions of the land and decides which restoration model we have to use. We have more than 60 models. But they typically fall into one of the 3 buckets. The one here in the left is an area that has probably been deforested 400 years ago. This is a site very close to where the Portuguese landed in Brazil in the 1500s. So it has been a sugarcane plantation, a cattle ranch. Has been planted with invasive species. You can see that the topsoil was eroded, very hard to restore. On the other hand, you have land in the Amazon. This is surrounded by forests, has been deforested probably 30 to 50 years ago. Very easy to restore. If you fence it, the forest will probably come back naturally. We have minimal intervention. In the middle, you have all the other 60 types of restoration. It depends on what kind of trees we have there, what kind of invasive species we have there, what kind of topography we there. So that's why we have so many different models to deal with typically with the median natural regeneration potential, all the sites in the middle there. That's a typical plan that's produced by the computer, by the model, deciding how to restore what type of restorations in each one of the points. So this is generated by the computer model, deciding space by space what type of restoration you have to do in the land plot. This is the same thing, a large area in the Amazon. And this is a little bit of the infrastructure we need to continue to scale up the process. We have a tree nursery. This is a premier tree nursery in Brazil. It's a tree nursery that can produce 8 million seedlings a year, but we actually don't use it so much as a high output nursery. We use it for research. This is very close to the University of São Paulo agricultural campus. It's a research center. We use it to research how to collect, store, germinate, and produce the best seedlings. And then we bring people that are willing to create a nursery close to the restorations in the Amazon and the Atlantic forest. we give them all the technology, we give them a long-term contract, and we incentivize them to set up a nursery. In this way, we have already incentivized the formation of 20 different nurseries across Brazil, and those are our suppliers that are going to help us to scale up to 1 million hectares. We also develop partners and third-party contractors in all different areas of ecological restoration, drone controls, drone for dispersing seeds, drone for controlling for invasive species, seed gatherers, field operators. We borrow from the pulp and paper industry in Brazil. That's the largest and the most efficient in the world, and they're planting eucalyptus, so we have to just adapt their systems to planting native trees. And we also have our own operations. Now, the last phase is actually selling the carbon credit. So we buy the land, we have all this trouble analyzing the land to buy the perfect land, the right land. We have all this trouble of producing seedlings, planting, recreating the forest, and then we have to sell the carbon credits. We have a very complicated process. Carbon credits are today what we call a voluntary market. People buy carbon credits voluntarily because they want to show the world that they're doing good, that they're carbon neutral. And in the past, companies were trying to buy any carbon credits, think this would help. There were a lot of scandals. Consumers and policymakers started complaining that it doesn't help if you're buying low quality carbon. So there was a rush to good quality carbon credit. So selling a carbon credit today is a lengthy process that takes typically 1 to 3 years of negotiating a contract. We talked to over 300 companies. We did due diligence negotiations, and today we focus on a handful of companies that are companies that go beyond carbon. They understand the merits of biodiversity, of how we deal with the local communities, and the other ecosystem service that we were providing by restoring the natural capital. We have already said what's called offtake contracts, meaning that our clients have the obligation to buy from us every credit that we produce. They range from 10 to 30 years, and they cover an area of 35,000 hectares of restorable land. So we have already restored 13,000, but we have contracts to restore 35. So we can continue to buy land and restore land because we already have the buyer that has agreed to buy everything we can generate for the next 10 to 30 years. Now, one critical element, I talked about permanence some time ago, meaning that if the forest catches on fire or is cleared again, we lose all the carbon that was captured by the forest growing up. And a key element for guarantee the permanence is the community understanding the value of the forest. If the community around the forest does not understand the value of the forest, there's a big incentive for them to cut down the forest, try to do something else, raise cattle, plant something. So engaging the community is a big part of what we do. And this is a very interesting chart. This is information just came out this week. I think this is going to pretty soon become an academic study, but we're just getting data. The blue bar is the income that all the employees of the farms we acquired had, and all put together. So every time we acquired a new farm, we count how many employees there were in the farm, how much money they were making, the wages, the salaries, and we add up to the blue bar. The other bar, the brownish and green, is how much the people that directly working with the restoration on the same land are making. So you see that in 24, 25, and the green bar on the top is bioeconomy. I'm going to talk a little bit about this. But you see that we are generating income for the communities that's 5 times the income they were generating when they were working for a cattle ranch. So it's a big boost in the income for the communities around. However, this is that's the headline, but there's a catch. The activity of restoration peaks after 2 or 3 years. And then the employment that the farms with the restored forest are going to have are not very different from the blue line, from the blue bar. So if we continue to scale for maybe 10 or 15 years, that's how we're going to show the company. We are a company that acquired land that had just a blue bar in terms of income for the people in the communities, and we're generating 5 times the income. I'm probably going to be able to brag about this for 10 to 15 years, but then it's going to go down dramatically. The way to avoid this to go down dramatically is to generate more income from bioeconomy. And so every site is different. So those are 6 projects that we have in that big site that we have in the Amazon. It's one of the largest restorations going on in the world. And we have 6 different projects for the local community to try to develop a bioeconomy in the region. I think the most interesting one is this one I'm going to talk about, acai. I guess everybody here knows what acai is, right? Well, acai can be produced in 2 ways. It can be a monoculture, or it can be collected in the forest. When we arrived and we bought the farm, we did what we do all the time. We got together with the local community and asked them what were their biggest concerns. Number one concern, they said, well, we have an informal arrangement with the farm owner that we can collect acai in the forest inside the farm. And we fear that you're going to either prohibit that, or you're going to charge us for collecting acai. And so we said, no, we're going to do exactly the opposite. We're going to help you collect acai. We're going to give you safety equipment. We're going to help you with the best routes to get in and out of the farm. We're going to help you organize yourselves in a co-op. And we're going to give everyone an identification tag so you know who is coming in and out, and you know how much is being taken, and you can keep all the profits. You can keep all the acai that you collect. And better, we're going to do an experiment of overplanting acai in the restoration we're doing right now. So when we finish the restoration, you're going to have much more than the double of the acai you currently have to work with. And by organizing themselves, they already found ways to get a better share of the value chain of acai. They were selling all the acai quickly to the middleman. Now they organize themselves and they are getting a better price. And with the volume they are extracting right now, and certainly with the volume they're going to have in the future, they're probably going to be able to process the acai in the community, package the acai there, and brand it with a brand that I hope is going to be the ultimate organic acai, collected, processed, and branded in the heart of the Amazon. So right now it's $100,000 operation. This can be multiplied maybe by 10 if they control a big chunk of the value chain of the acai. And this can be done to many other products. They're doing this to honey, to other seed collections, to other things that we can find in the forest. That's photographs all taken in the restored area. None of this is taken in the in nearby forests. Those are all trap cameras in the restoration area. Thank you.